Good afternoon. Okay, today is my last lecture. Right, so we will finish the remaining materials. Then after that, I will give you a quick summary. Right. Okay, yesterday we have discussed basis path testing techniques. In applying basis path testing techniques, there are 3 steps after you draw the control flow graph. Okay, calculate the psychometric complexity V bracket G equal to E minus N plus 2. Alright, then use this number as a guide to identify a basis set of linearly independent path in a control flow graph. Right, once you have identified a set of basis set of linearly independent paths, then we design a test case to exercise each of them. Okay, it's something like solving simultaneous equations. Okay, now so we have finished everything actually except the example. So today we start from this example here. Okay, we based on the same piece of code that we have drawn the control flow graph. In this case, psychometric complexity can be easily calculated. Is 3 is equal to 3. Here I use CC to denote psychometric complexity. The standard notation is V bracket G. Alright, and in this case, very clear there are 7 nodes, and you can calculate they are altogether 8 edges. 8 minus 7 plus 2, that is 3. So that means the next step, we will identify a basis set of linearly independent path. We should have 3 paths. Okay, we start from the shortest. The way to identify a basis set of linearly independent path is always include the shortest path through the control flow graph first, from beginning to end. Okay, the shortest one. Okay, this is the shortest path here, 1, 2, 7. So this is the first path we include. You must include the shortest. If you do not include if you do not start from the shortest, you may make mistakes. Then after that, we see whether our set of path has passed through all the nodes and edges. If it has not, we have to continue to include path. Okay, in our set. Okay, after we have included 1, 2, 7, obviously there's a lot of nodes and edges. We have not, our set of path has not passed through yet, so we include some more. The next one, when we want to include the next one, always based on the previous one, make a minimum change to the previous one. So when we want to include the second one, the previous one is the first one, 1, 2, 7. Since the first one get out from here, follow this branch. So you make a change here, 1, 2, 3, 4. After you make a change here, okay, you should follow the previous path as closely as possible. But in this case, there's no way to follow the previous path because the previous path go out from 7 already. Okay, so once you cannot follow the previous, you have free of choice. That means the second path can be 1, 2, 3, 4, 6, 2, 7, can also be 1, 2, 3, 5, 6, 2, 7. Okay, which one you include first as a second path is both correct. So after we have included the second, okay, when you include the second path, once you come to 2 again, you have to follow the previous path as close. So you have to get out. You must be 2, 7. Okay, you cannot go through one more round because you can follow. That is a minimum change. Then after you have included the second path, you will find that you have not covered all the nodes and edges yet. So we have to add in some more path. Then we include the third one by making a change to the second one. So by doing so, we have 3 paths. After you have the third path, you find that our set of path has passed through all the nodes and edges. So that means we should stop. We should stop. That is our basis set of linearly independent path. Okay? And earlier we have computed psychometric complexity. That is 3. Now we have constructed a set, also a 3 paths. That means your answer likely to be correct. If your number of paths does not tally with the psychometric complexity, definitely your answer is wrong. Okay? Then after you have your set of paths, for each path, we go back to the control flow graph, go back to the code to find input value. Okay, in this case, the input is I and Y, since read IY, and the output is AB, since the program print AB. All right, so we go back, for each path, we go back to the control flow graph, go back to the code to find input value to satisfy the condition of branches that the path pass through. Okay? The condition of all the branches that path pass through. This step, the third step, okay, is the same for all the three basis paths, for all the three structural testing techniques. Okay? After you identify a set of paths, for each path, you design a test case. Okay? For each path, you design a test case that is exactly the same for all the three basic structural testing techniques. Okay, before we go further, I would like to highlight to you that if you do not start from the shortest, you will make a mistake in this case. Okay, let's say the first one you don't include 1, 2, 7 the shortest first. You include 1, 2, 3, 4, 6, 2, 7 first. Okay, let's say you ignore this one. You do not start from the shortest. After you have included 1, 2, 3, 4, 6, 2, 7, you find that you have not included, your set of path has not passed through all the nodes and edges yet. So you will add in the third one. You are based on this first one. Now this is the first one. Okay, we did not include the shortest. We start from this one. So after you have this one in our set, we find that node 5 have not passed through by the set. So we have to continue to add in path. We add in the third one. 1, 2, 3. Okay, you make a change here. 5, 6, 2, 7. Okay? Then you find that your set of path has already passed through all the nodes and edges. Yeah. Then you will stop here. By doing so, you will only get 2 paths instead of 3 paths. Okay? So this is the case I want to show to you. Okay, now the next 2 slides will highlight to you some of the property in the control flow graph we can study systematically, right? So every time when you execute a program, okay, the program will follow one of the execution paths. That means start one of the paths from begin to end. Okay? So every time when you execute this program, you will follow either this path, or this path, repeat the route many times, then get out. Okay? You will follow one of the paths. Okay, in general, when a control flow graph has a loop, okay, there are infinite number of paths in the control flow graph. Even this simple control flow graph, there are infinite number of possible paths. Okay? It is not just 3 paths, because a path can go through this loop 1 time, 2 times, 3 times, 100 times. Okay? So there's many, 1 million times, there's a lot of possible paths in this control flow graph. So in total, there are infinite number of execution paths in this program. Okay. But for this control flow graph, earlier we have already calculated in terms of number of paths in the basic set of linearly independent paths, we only have 3 paths. Although altogether in total there are infinite number of paths through this control flow graph, but we only have 3 paths in our basic set of linearly independent paths. Okay? So for this particular control flow graph. Okay, now we want to see an example to show you how to study some more property in control flow graph. Okay, so again, the same control flow graph. Although there are infinite number of paths in this control flow graph, but we study a few cases here. Case 1, we take a look, we analyze this graph to see how many paths in this control flow graph without going through the loop, did not go through root. Oh, there's only one path, right? There's case 1, so we can identify without going through a loop. The loop is here. The loop is here. Without going to the loop, that means just go out straight away. Only one path. That's case 1. Case 2. Do not repeat the loop. Do not repeat the loop. That means go through the loop at most one time. Without repeat the loop, that means you will go through loop, but when you go through loop, you will go through at most one time. Okay, that means go through at most one time. At most one time can be do not go through the loop or plus go through the loop one time, right? So case 2 actually is case 1. Case 1 without go through the loop plus another subcase, that is go through the loop exactly one time. Because what we are interested here, case 2 is go through the loop at most one time. At most one time, that means do not go through the loop or go through the loop exactly one time. Okay? Without go through the loop, we have already calculated in case 1, there is one path. Okay? And go through the loop exactly one time. When you come here, there are 2 alternatives. So it's 2 paths. Go through the loop exactly one time. Altogether, there are 2 paths. So in total, for this case, the total number of paths is 1 plus 2. Okay, now we can further study another case. Repeat the loop at most 1. That means now we go further. Earlier we say do not repeat the loop. Now we allow the repetition of loop, but at most one time. That means go through loop at most 2 times without repeat the loop one time. Repeat the loop at most once. That means go through the loop at most 2 times. That means the first time you go through loop is not considered as repeat. So again, this case can be further divided into 2 subcases. That is case 2 plus those go through the loop exactly 2 times. Because now what we are interested is go through at most 2 times. At most limit can be exactly 2 times or those less than 2 times. Those less than 2 times is case 2. So case 2, the number in case 2 plus go through the loop exactly 2 times. Go through the loop exactly 2 times. How many paths? Okay, the first time when you come here, there are 2 alternatives. Okay? Then when you go back, the second time when you come here, again there are 2 alternatives. So altogether there are 2 times 2 paths, 4 paths. Okay? 4 paths, go through loop exactly 2 times, plus case 2. Case 2 there is 3 paths. So 3 plus 4, there is 7. Okay, we can continue to study case 4. Repeat the loop at most twice. Repeat the loop at most twice means go through the loop at most 3 times. Okay? The first time you go through, it is not considered as repeat. Go through exactly at most 3 times. That means we can further split into case 3, the earlier case, okay, plus those cases go through the loop exactly 3 times. Because now what we are interested is go through the loop at most 3 times. Okay? So for those cases go through the loop exactly 3 times. The first time you come here, there are 2 choices. Second time come here, also 2 choices. Third time come here, again there are 2 choices. So it's 2 times 2 times 2 paths. Go through the loop exactly 3 times. Altogether there are 8 paths. So 8 paths plus those cases calculated for case 3, that altogether is 15. So you can continue to study. You can continue to study to find out the number of paths that repeat the loop at most 3 times, at most 4 times, etc. Okay? You can even derive a formula using mathematical induction. Okay, now I would like to highlight to you another property for path in control flow graph. Okay, those paths that we have seen in our example, okay, we can always design a test case to exercise it. That means we can always find input value to satisfy the condition of all the branches that the path passed through. Right? So actually, not all the paths behave this way. That means sometimes you may have, when you apply testing techniques, you may encounter a path. No matter how, there's no way for you to define input value to satisfy the condition of branches that the path pass through. Okay, so you may encounter such thing. It's quite logical, right? Earlier I told you that to find input value to satisfy the condition of all the branches that the path pass through is something like solving a set of simultaneous mathematical equations. So when you solve a set of simultaneous mathematical equations, you may not get a solution. For some of the equation, you may not get any solution, right? So likewise, when we try to find input value to satisfy the condition of all the branches that the path pass through, we may not be able to find any input value for some path. Okay, those paths we call them as infeasible paths. Okay, those that we can find input value to satisfy the condition of all the branches that the path pass through, it means we can design a test case to exercise it. We call them as feasible paths. So there are two kinds of paths. And this slide, we have seen a number of feasible paths in our example earlier. Okay, this slide gives you an example of infeasible path based on this small piece of code here. Okay, for this small piece of code, I is the input value. I is the input variable. All right, you take a look. These two paths are both infeasible. One in this control flow graph, 1, 2, 3, 4, 5, 6. 1, 2, 4, 6, both are infeasible. That means there's no way for you to find I to satisfy the condition of all the branches that this path pass through. We take a look at the first one. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. Okay, this path. Okay, so in order to exercise this path, you have to, altogether there are how many branches? 1, 2, 3, 4. There are 4 branches. This path pass through 2 branches. Okay? So in order to find exercise this path, that means you have to find input value I to satisfy the condition of all the branches that this path follow. That means condition of this branch and this branch, because this is how the first path. Okay, 1, 2, 3. 1 from 1 go to 2 go to 3. In order from 1 go to 2, this branch, 2 to 3, this branch, that means I have to be greater than 5, right? So that means this condition need I to be greater than 5. Okay, you have to identify I which is higher than 5, greater than 5. And after that come to 3. 3 we set the J to 4. We set J to 4. Okay, you have an I, you must define I greater than 5. And J will be set to 4. Okay, so when you come here 4, because this path go by 4, 5, so it has to satisfy the condition of the branch, this branch, 4 to 5, 4 to 5. That means the condition, this is the condition, I plus J must be less than 8. Okay, I plus J must be less than 8. So there's no way for you to find the value of I. Earlier, this, in order to satisfy this condition, I have to be greater than 5. And once you go to 3, J will be set to 4. So that means I plus J at this point in time will definitely greater than 9. There's no way to be less than 8. Okay, so there's no way for you to find I to satisfy the condition of this branch and this branch concurrently. Okay, so this is an infeasible path. There's no way for you to exercise this path. Okay, when you apply a testing techniques, if you encounter such situation, what to do? Okay, we will simply do not consider that path. Okay, so you may have in your basic set of linearly independent path, you may have 10 paths. Okay, out of it, it could be one path which is infeasible. If that is the case, then you point it out and you only design 9 test cases. Okay. The reason is very clear again, okay? Since there's no way for you to find input value to satisfy the condition of all the branches, that means subsequently when the user runs the program, that path will not be exercised, okay? So we need not to test the path, okay? So that is the reason behind. Okay, the next 2 slides will introduce a very simple measurement to measure how good is a test suite. How good is a test suite? Okay. So the measurement we are going to introduce still based on the three aspects we address in the three structural testing techniques. That means based on the statement aspect, based on the branch aspect, based on the basis path aspect. But one point I would like to emphasize here is this measurement coverage analysis is not only to measure test suite design from structural testing techniques. Okay, they can be used to measure any test suite. Okay, any test suite. It means even if you have a test suite designed randomly without using any method, you can use this coverage analysis to measure the quality of test suite also. Okay, so the measurement, the name of the measurement is called structural coverage analysis. Okay, and it's based on statement, branch, and basis path aspect. Okay, the first measurement, statement coverage. Okay, statement coverage is based on statement aspect. Okay, so for statement coverage, what we measure is after you run the whole test suite, if you want to measure by statement coverage, then we will calculate the percentage of statement that our test suite has exercised. Okay. If your test suite has exercised 100%, if your statement coverage is 100%, that means your test suite is quite good from statement aspect. If your test suite has only exercised that 5% only, that means your test suite is not so good in terms of statement coverage. Okay. So the other one is branch coverage. Okay. Also quite similar. The way we compute is the percentage of branches that your test suite exercise. So that is a branch coverage. Basis path coverage, likewise, is the percentage of basis path. Okay, we have your test suite has exercised. If your basis path have three paths, if your basis set have three paths and your test suite only exercise one of them, that means the percentage should be 1 upon 3, 33.33% only. Okay, and the logic for using this measurement is very clear. If we have a test suite, you have exercised, you can exercise all the branches, that means your test suite is quite good. Okay, that is quite intuitive. Okay, and in practice, this coverage analysis is also quite useful, and quite a lot of commercial software testing tool can compute it automatically. When you use a testing tool, that means you will conduct your testing under the tool, and when you run the test cases, the tool will track the execution, will trace the execution of the program. At the end, okay, the tool can compute automatically, see how many statements that your test suite has exercised, the percentage of statement or the percentage of branches or the percentage of basis path, etc. Okay, here we have a simple example to show you how to compute these three coverage. We based on the same control flow graph. Okay, firstly, this is our example test suite. Okay, assuming that we have a test suite, just have one test case, just have a single test case. As such, here, input I equal to 99, Y equal to -1, expected result, this is expected result. Okay, we just one test case only. By running this test case, you can see that I equal to 99, Y equal to negative, so you exercise this path. You will certainly exercise the program through this path, 1, 2, 3, 4, 6, 2, 7, okay? That means you will go through all the nodes except node 5. That means you will exercise every statement except the two statements under node 5. And two statements here, 5, okay? So statement coverage means that the total number of statements exercised by this test suite, that means those statements under all the in all the nodes except node 5. Okay. So in this program altogether there are 14 statements. In total there are 14 statements. 1, 2, 3, 4 you can count. But when you count, be careful. Don't count else. Don't count N if, okay? Don't count N while, because N if and else is considered as under if, okay? Together as one, count as one statement. N while is considered as one statement together with while. So you should not count else, N if, N while. You can check that all together here got 14 statements. Then by running this test suite, only this node is not exercised. That means only 2 statements under node 5 is not exercised. So 14 statements in total. Out of it, it exercised 12 statements, 14 minus 2. So the percentage of the statement coverage is 12 divided by 14%. Okay, that is 85.7%. Okay, in terms of branch coverage, because this test suite will exercise program through this path. Okay, so in total, altogether, how many branches in this control program? There are 4. This have 2 decision nodes here. All the outgoing edges are decision are branches. So altogether, 1, 2, 3, 4. 4 branches here. And this test suite exercise 3 branches except this one. So in terms of statement coverage, in terms of branch coverage, is 3/4%. That is 75%. Okay, in terms of basis path coverage, earlier we have already calculated the total number of basis paths is 3 paths. Okay, and this test suite exercise only 1 of them. So in terms of basis path coverage is 1/3. That is 33.33%. Okay, so this is a simple example to show you how to compute coverage analysis. Okay, we have almost covered all. Okay, the next few slides, I will just give you a very quick overview of the overall testings. Okay, in general, software can be structured into 4 levels: unique, component, product, and system. Unique is the lowest level. When you write in C, when you use C programming, unique are those things like function, procedure. Okay, those are unique. So we combine many unique together to form components. We combine the related unique together to form component. Then we combine a number of components together, related components, to form a product. And you may combine a number of products together to form a system. So in general, software can be structured into these 4 levels. So when we conduct testing, we have to test each level. We cannot just test one level. That means we have to test, initially we have to test the unique level, the lowest. Unique is the lowest. Then component, product, and system. Usually we will start from the lowest to the highest. Okay, process of testing. Okay. So when we conduct testing, usually the first thing we do is functional testing. And functional testing, you can see that are easier to apply. In fact, in the industry, in practice, testers depend very much on functional testing. Okay. Structural testing are hard to conduct unless we use automated tools. Okay, so ideally we should conduct functional testing, then after that conduct some structural testing to supplement it. And in terms of level, we should start from the unique level, start from the lowest to the highest. Okay, so this is in terms of structure. Okay, in terms of process, testing process, how to carry out a testing. Usually we adopt a sequential waterfall model. We start from planning, then design test cases is an important thing. Okay, we have spent most of the time to learn the basic method for designing test cases. Then implementations. Implementation means that if you have a very big project, okay, to test a very big system, sometimes you may have to develop some software to assist the testing, okay, to automate those tedious manual tasks in order to carry out efficiently. If you need such development, then that will be done under test implementation. Then after that, test execution, you run your test cases, execute your test cases. Then do execution. After you execute your test cases, compare the expected result with the result reflected from the test cases. Then do analysis, then documentation, and final reporting to determine the readiness of the project. Okay, so we have to test all levels, unit, component, product, and system. So you can see from here that from component onward, okay, all can be considered as higher level testing. Unit is the lowest level, okay. So there's nothing lower than that. So from component onward, all considered as higher level testing, okay. So in this higher level testing, okay, because we have already tested the lower level, so when you conduct higher level testing, our emphasis is integration, okay, to see whether when we put the lower parts together, they can work properly, they can interact properly, they can interface properly. So the emphasis, the primary objective is on integration testing, to see whether there's any interface error, any interaction error. So in terms of conducting integration testings, this slide lists out some commonly used approach. Okay. Top down, the first one. That means you test the top one first. Let's say if you have function A call function B, okay. Invocation hierarchy. Invocation means calling structure. Okay. So if you have function A call function B, function A is at the top. Okay. That means you test function A first. That is top down, according to invocation, calling structure down. Bottom up means the other way around. If A call B, you test B first. Okay. Those at the bottom first. That's another approach. Then risk-driven, test the more risky one first. Okay, so that you can sleep better. So, and schedule-driven, depending on which one we want to implement first, we test it first. Function-driven, that means test by use case in terms of object-oriented approach. Hybrid means a combination of them, a combination of all these approach. Actually, the most commonly used is the hybrid approach. Okay, in practice, it's hard to just go solely based on one particular one. So usually you will apply a hybrid approach. Okay, now I want to say a few, highlight some points on OO, testing OO system. Okay, when you apply object-oriented approach to develop software, okay, the basic functional and structural testing can be applied. Okay, that's why we call them as basic fundamental. They can be applied to all software. But I would also like to highlight to you that some features of object-oriented languages cannot be sufficiently tested by the basic methods. Okay, so need special method to deal with it, to test it. Things like inheritance, things like polymorphism. Okay, cannot difficult to be tested by basic method. Okay, but we will not discuss those methods. Okay, under this course. Okay, the last slide, I would like to highlight to you some common terms, okay, in testing. First, regression testing. Regression testing is a very common word. Okay, after you have implemented software, after you have completed your project, after user install for the user to use it, okay, so subsequently when the user requests for some changes, after you have incorporated the changes, make the changes, okay, then the developer will have to do a regression testing. Cannot just test the part that he has changed. Okay, he will have to test more than the part that he has changed, because the changes may affect the changes may affect other part of the systems. So if we have to conduct testing not only on his part, but all part that can may be affected. Okay, so that kind of testing is regression testing. Okay, so that means in practice, after you have installed the system, when the user need any changes, if the developer incorporated the changes, then we have to conduct a regression testing, not just testing the part he has changed. Okay. Acceptance testing. Okay, acceptance testing is user formal testing, where after a software vendor develop a system, when he want to deliver to the user, okay, and to complete the contract, then we have to do an acceptance test. We have to do an acceptance test to accept the system first. Alpha and beta testing. Okay. Alpha testing is the actual end user testing performed within the development environment. Okay. End user come to do an actual testing to simulate, okay, the actual operation, but it's under the development environment, so that it will not affect the existing operation of user. Okay, so that kind of testing is called alpha testing. Beta testing is more advanced than alpha testing. It's the end user testing to simulate the actual situation, but it's conducted in the user environment. Okay, so that is more advanced. Okay. And if you look at open source software, there's a lot of open source software. Okay, you may see that some of the software claim themselves as alpha, some claim themselves as beta stage. Those beta stage are more advanced than alpha. Okay, that's all for my lecture, but before I end it, I would like to give you a summary here. Okay, in terms of Unit 1, the emphasis is basic process model. I think I have mentioned that when I go through Unit 1, the characteristics, okay, the differences, and how to select them when given for a given situation. You have some simple question in tutorial 1. I will post it to the website. Don't need to take picture. I will post it to the website after this. Yeah. Okay, so you have some question in tutorial 1, given a situation for you to choose a more suitable process model. Okay, Unit 2, we talk about ER modeling, we talk about DFD modeling. For both modeling, the basic concept, I think we have quite a bit of question in our quiz on the basic concept. Okay, using basic concept to choose a basic concept to model, the more suitable basic concept to model a list of given items, okay, and apply to small case. Okay, so all these I emphasize small case. That means you will not be given a case with one-page description. Okay. Ask you to draw an ER diagram, or you will not have such questions. Okay, small case means something like your, for example, something like your the DFD modeling would be something like this one question asks you to draw a DFD diagram for distance learning education. Draw a DFD for distance learning education. I think it's one of the questions in tutorial 2, tutorial 3, I guess. Yeah. All right. So small case is something in along that line. Okay. And also ER modeling is also small case. Unit 3. Class diagram, again on basic concept, you have some question in your quiz also, and apply to small case. Okay, in terms of, I give you an example on the small case. What does small case mean for class diagram? Okay, something like one of the example you have seen in lecture notes. the example on the last page of your Unit 3 lecture notes, right? Unit 3 lecture notes. And another example will be things like, in tutorial, there's one question asks you to draw a class diagram to model the various types of graphics object, right? Things like a document is composed of several sheets and those things, and geometrical object can be further used. So it's that kind of case, all right? I think I've given you sufficient example. Unit 4, drawing use case diagram. Draw use case diagram for small case. Here I did not mention writing use case description. So that means, I hope you know what I mean, yeah. All will be covered, is written down here. So state diagram applied to small case is something like this week, the tutorial question 1 and question 2, that kind of case. All right. Then Unit 5, we have basic and brief understanding of USDP to see how USDP is carried out. That means exactly those things written in Unit 5, the notes. Okay. USDP requirement analysis. What kind of techniques used for requirement capture? Take for example, we use case diagram, right? And we write use case description for each use case. And in addition, we may create some activity diagram and sequence and state diagram, okay, to help to supplement the description of use case. So those things, okay, you need some basic understanding. And as I said earlier, I will not have any question on activities and sequence diagram. I will not have any question ask you to draw activity and sequence diagram. Okay. The objective of introducing you activity and sequence diagram is to help you to have a brief understanding of USDP, how USDP is carried out. Okay. And all my tutorial, okay, I have 7 tutorials, tutorial 1 to tutorial 7, okay. So these 7 tutorials are sufficient for my part, okay. So remember the words, yeah. That means if you see any other thing from other part, okay, those are not for my part, yeah. Those are not for my part. That means you will definitely not see any case that asks you to draw activity diagram, sequence diagram, yeah. Okay, now come to Unit 6 excluded. Unit 6 is not included. Okay, Unit 7 and Unit 8, almost the whole unit are important. Basic concept, the testing, the type of testing techniques, okay, structural and functional testing, what they based on, and the 3 functional testing techniques. Okay, I told you they are very important. They are very important, okay, for your exam and also in practice. Yeah. So learn them. Yeah. And Unit 8, again, all are important except the last part. The overall approach. Just now I said I will go through briefly that part. Not so important, yeah. Okay, and apply, know how to draw, and all the code that you are going to see will be structured. Okay, you can apply the rule, etc. All right, and okay, now, okay, in terms of past year papers, okay, only 2006 and 2007 onwards are relevant. Okay, the other thing is that, okay, that is all for summary, but I would like to say a few words on the quiz also. Yeah. Is it okay? Any question? Okay, that's all. Okay, in terms of quiz, I will not go through the answer because the quiz are not so difficult. Okay, but one point I would like to highlight to you is that I have mentioned that more than one time during the lecture. Okay, all the concept things like multiplicity, like association, aggregation, all this have a precise meaning. Okay, I strongly advise you to go through the meaning and follow the definition precisely. Take for example, for multiplicity, okay, I'll go through the definition in Unit 3, page 14. I can even remember the page number. Unit 3, page 14, the definition of multiplicity. Go through it, and when you see a diagram with multiplicity, just interpret according to the definition. Do not add in your own intuitive impression, right? I also mentioned to you earlier that, okay, sometimes a concept can be harder to understand because you see only a notation 1 to 2, you will interpret in your own way. Yeah. That was certainly out of track. That was certainly out of track. I advise you again. So I think quite a number of you make mistake in quiz for that kind of question due to that concept. Yeah. So understand it correctly. Do not just look at the diagram, say here is 0 to 1. Okay, that means this one not involved, that one not involved, that kind of thing. Do not. Precise meaning, it means that you interpret according to the definition, not less and not more. Yeah. Not less than that and also not more. Yeah. More also wrong. Yeah. You cannot add in your own impressions. So earlier I also tell you that a concept can be harder to understand than mathematics because we are all human. Okay. Human, when look at notation, nothing. Okay, I just interpret according my way. Yeah. Simply. So we are looking at a model. We are not looking at a piece of art drawn by an artist. Yeah. So you have your own imagination, your own interpretation. All right. So if you look at mathematics, something very complex. Okay, there's no way for you to interpret in your own way. So that make it easy. That make it easy for you to understand because you have to force yourself to understand it. Okay, that is the difficulty I emphasized before. I re-emphasize now again. So if you clarify that part, I don't think it is very difficult to understand. All right, I think that's all for my lecture. Yeah, although the lecture ends, but if you have any question, can always make an appointment with me and email me anytime. Yeah, I will certainly respond to you. And thank you very much for your cooperation. Yeah, thank you for your cooperation and for your attendance. Yeah, I can't imagine if I have just a few students here. Okay, how it will be harder for me to do my best. Because I'm a human too. Yeah. Yeah. So harder for me to do my best. That means the recorded lecture quality will be affected also. Those people who want to play the recorded lecture, yeah, may see a different quality also. So thank you very much for your cooperation. Yeah.